So I'm going to talk about a new method for dynamic community detection that we developed with Jean-Charles Delven from the Université Catholique de Louvain and Renaud Lambiat from the University of Oxford. So as you know, temporal networks allows to capture complex temporal patterns that are not well represented by static networks, such as the burstiness or memory or non-stationarity. And for example, here you have an example of non-transitive interactions. So if you have this small network with 3 nodes and 2 edges, you see that if first this edge between A and B is activated and then the edge between B and C is activated, it means that you can go from A to B to C following a time-respecting path, but you actually cannot go from C to B to A. So if you represent this as a static network, you lose those kind of information. So there are different ways to represent temporal networks. For example, what we use here is the so-called interval graph representation, where time is continuous and edges have a duration. There are also many methods to do community detection in temporal networks, but actually most of them aggregate the temporal dynamics over time, some time windows, or rely on the assumption of an underlying stationary process. And here we wanted to develop a method that didn't use any of those assumptions. Actually, what we ask ourselves is really what is the meaning of community in a temporal context. So in a static case, we have associative communities that are usually defined as densely connected group of nodes that are more densely connected to each other than to the rest of the network. And this actually implies a symmetric relation between nodes. But now if we look at a temporal network, the concept of density of connection actually must be considered over a time range, because if we look just at an instantaneous time shot, usually the network is very sparse, and also interactions usually take time over some time range. But now, if we look over a time range, as I showed before, the relations between the nodes are in general asymmetric. So here our idea was the following. We want to develop a method where we don't use any temporal aggregation, and we want to compare a synchronous evolution of a diffusive flow on this network, without making any assumption on the stationarity of this process. So first, how can we model a diffusive flow on a temporal network? Well, we can use this model of the continuous time random walk, where random walkers jump from nodes to nodes, and their jumps are restricted by the activation patterns of the edges. And they also have a constant rate of jumping, lambda, or if you want, a waiting time, 1 over lambda. And then, actually, if you look at this network with 3 nodes, A, B, C, and 6 edges, so you see that here, for example, random walkers can jump from node C to node B between T1 and T2. And actually, during this time, we can compute the transition probabilities. Actually, for each static inter-event times, we can compute the transition probability as the exponential of the Laplacian. And then if we want to know the transition probability between any 2 times and any 2 nodes, we just have to multiply those inter-event transition probabilities. And in general, this is a process that is non-stationary. We don't know if it will eventually reach a stationary distribution. And then what we want to do is cluster this flow to find clusters that are meaningful. And to do that, we actually can use the covariance of the random walks. And this comes from the idea that we want to define a good partition as a partition where random walkers are more likely to remain within the starting cluster, which is actually the framework of the Markov stability for static networks. But here we have a temporal network, so to express this goodness of a partition, we can use the covariance of the random walk process, which look at the expectation of the process at T1 and at T2. So we want it to be high because we want the random walker to be in the same, to stay in the same cluster, minus the same thing for 2 independent random walkers. But here we don't make any assumption on the stationarity of the process. which means that the covariance depends on T1 and on T2. Now we can define the density probability vector at time t and the transition probability matrix between 2 times T1 and T2. And using that, we can actually compute a temporal covariance matrix for between T1 and T2, which is defined as this. And here, if you look at element ig, you see that this is exactly the joint probability of being at node I at T1 and node j at T2, minus the same thing for 2 independent random walkers. But here we have a problem because we are actually comparing 2 nodes at different times. And this is not really something that we want to cluster nodes together. So how can we find a solution to this problem? Well, we can define a forward and a backward covariance using the inverse process transition matrix, Tinv, which actually is the matrix that if you start the process at T1 and let the diffusion happens until T, then it's the matrix that will make you come back from T to T1. And you actually can find it using Bayes' theorem. And now, using that, we can define the forward covariance. So we take the covariance and we multiply it by this matrix Tinv. And what we have is a process that starts at T1, evolves until T, and then goes back to T1. But if you look at element ig of this matrix, you see that we have now the joint probability that 2 walkers start on I and j at T1 and are on the same node at T, minus the same probability for 2 independent random walkers. And similarly, we can define a backward covariance. If now we look at a later time T2, and we let the process diffuse but backward in time, so you're using the reversed evolution of the network until sometime t, and then we go back to T2, we have now this backward covariance. So now we can have a way to compare nodes that is synchronous, so we look at the same time. We also have symmetric matrices and a process that is not necessarily stationary. So now if we have a time range T1 and T2, we can define 2 quality functions as the integral of those covariance matrices, and then we cluster them using those 2 indicator matrices, HF and HB, which encodes the forward and the backward partitions. And the goal is to find the partition that will maximize those 2 quality functions. And this gives us a clustering in terms of sources for the forward partition and sinks for the backward partition. So to give you a few examples, here we have a dataset which records the contact between 3 living wild mice that live in the countryside freely, but they record the interaction when they are inside nests. So this is 2 months of data with a very high resolution. And what we did is that we look at weekly intervals, and for each week we start a random walk process with a uniform initial conditions, forward and backward, and we find the forward and backward partitions. Then we can run that many times and look at the variation of information of the partition that we find. And when we have minima of the variation of information, it actually means that we are looking at robust dynamic scales in this system. So here, just to show you an example, if we look at a random walk waiting time scale of 1 second, we find this evolution where we have here for each week the forward and the backward partition. And here actually we go from winter to spring, so from cold weather to warm weather, and from a case where there's no reproduction and actually no competition between the mice, to a case where reproduction has started and there's not a lot of competition. What we see is that the groups, the communities are first very large in winter, and then they split as a competition between the different mice rises in smaller and smaller groups. But what is very interesting is that now if we look at a different dynamic scale with a waiting time of 24 hours, we see that here we have quite different pictures with communities that are extremely stable with time, which means that actually there's also very stable social groups in this system. And to give you another example, here we use the possibility of this method to actually also use non-uniform initial distribution. So in this case, we use that on the APS co-authorship network to find the physical influences of network scientists. So we actually found all the network scientists that published in a journal of the APS between 2000 and 2010. And starting from those authors, we actually let random walk diffuse backward in time until the 1970. And for each decade, we apply now the backward flow stability to find a backward partition. So if you look at what we find, here, if we start from the 2000s, we have, for example, here just 3 communities, and then we can look at who are their ancestors. So if we look at the partition of the 90s, even if it's not the same nodes in the partition, we can actually link them through the transition probability. So the probability to start in one of those partition and be in one of the community of the 90s. And you see that the communities are quite different in terms of the main journal in which author published, and also in terms of the keywords that are used in the title of those communities. And as we go back in time up to the 70s, we see that we only have now just 3 big communities that also are quite different in terms of journal and keywords. So yeah, just as a conclusion, we have these temporal flow stability methods that cluster the forward and backward flow of a random walk, doesn't make any assumption of the stationarity of the process, and has this dynamical resolution parameter. And we think that it really opens the door to define new concepts for temporal networks in terms of random walk and flows. So thank you very much for your attention.